So, Saili, are you there?
Yes,
Saili?
ma'am.
Yeah, okay. How many participants have joined till now?
6.
Okay.
They will be soon joining. At least they'll need 6 to 6 5. It will be session will be started, I guess, ma'am.
Oh, resource person has joined?
Uh, I guess, ma'am. Yes. No.
Okay. Okay, make sure like put a reminder message in WhatsApp. Make sure everybody joins on time.
Yes, ma'am. Sure.
Okay, okay. I mean, welcome.
Hello, Anita ma'am. Are we audible to you?
Yeah, yes, ma'am.
Okay, welcome, ma'am. We'll
Yeah.
soon start the session after everyone joins.
Okay.
Thank you, ma'am.
Anita ma'am.
Yeah, hi.
Good evening, ma'am. How are you? This is
Hello,
Dr.
hello, ma'am.
Sanjivani University Dean.
Okay. Okay.
Yeah. Okay. Fine. So we'll wait for some time, Siley. Just make sure the participants are joining on time.
Yes, ma'am.
Yeah.
Good evening, everyone. It is with a great pleasure that I welcome our respected Dean, Kavita Rani, and all the participants to the online faculty development program on predictive analytics and optimization for industrial application, organized by the School of Engineering and Technology, Sanjivani University, in collaboration with Finessefleet Foundation, Bangalore. Before starting the session, I would like to read some guidelines to you all for today's session. First, the session is being conducted via Microsoft Teams and hosted from Finessefleet Headquarters, Bangalore. After the session concludes, a recorded version will be made openly available and a consolidated list of recordings will be shared via email. Second, a dedicated Q&A session will take place at the end of the talk. Participants are requested to hold their questions until then. However, you may submit your queries in advance through the Q&A section, which will be moderated. Third, video and audio must remain turned off unless you are speaking. If you wish to speak, please use the raise hand feature and the moderators will grant you the opportunity. Fourth, attendance will be recorded through a dedicated form which will be shared during the session. Kindly ensure that you mark your attendance by filling out the form when it will be asked. The form was already on the screen displayed and the link of that form will also be in your chat box. Please do mark your attendance. Fifth, following the keynote talk and Q&A session, a networking session will be held. Participants are encouraged to connect with peers for discussion on potential research collaborations, teaching areas, and brainstorming session. Please maintain professional decorum and adhere to ethical communication standards. Sixth, after the session concludes,
Shaili, you are not audible. You are on mute.
am I audible, sir, now?
Yeah, you are audible. Please proceed.
Yes.
I'll reread the last two guidelines for you all again. Following the keynote talk and Q&A session, a networking session will be held. Participants are encouraged to connect with peers for discussion on potential research collaboration, teaching areas, and brainstorming sessions. Please maintain professional decorum and adhere to ethical communication standards. After the session concludes, do not leave immediately. The host or moderator will end the meeting for all the participants. We are gathered for yet another insightful session, and it is truly an honor to welcome our today's guest, Professor Anita Rajam. She is a professor in the Department of Computer Science and Engineering at Anna University. She holds a PhD in Networks 2010 from Anna University, an ME in Computer Science and Engineering 1997 from Manonmaniam Sundaranar University and a BA in Electronics and Communication Engineering from Bharatiya University. Her research focuses on image processing, wireless networks, cybersecurity, in artificial intelligence, and trustworthy AI. She currently serves as head of department and director at the Center for Cybersecurity. She is a life member of ISTE. In today's first half of the session, she will be delivering a keynote talk on artificial intelligence and machine learning and introduction to AI security. As we are in the virtual mode, ma'am, so please accept a token of appreciation which is presented to you for your contribution to the Faculty Development Program 2025 as a keynote speaker held on February 2025, enriching the academic discourse and fostering knowledge advancement in the field. I now please request you, ma'am, to take over today's session. Thank you so much.
Yeah, thank you for the introduction. And I'd like to know, like, how long will the QA be and how long my presentation should be?
Ma'am, the presentation is till 8 o'clock. So Q&A must
Okay.
start before 8, like 10 to 15 minutes before, or as
Okay.
per your time. It's preferable
Okay.
as per you.
Okay. Okay. Okay.
Thank you, ma'am.
Thank you. Yeah, can you please stop sharing the screen and share my screen? Is my screen visible?
Yes, ma'am.
Yes. Is my screen visible?
Yes, ma'am, it's visible. Please proceed.
Yes,
Okay.
yes, ma'am, it
Okay.
is visible.
Thank you. Thank you. Okay. So today I would like to give details about AIML and introduce you to security issues for in AI. So that is going to be my agenda. I'm not sure how many of you are from computer science. Are there people from non-computer science background in this group? I see there are
Yes,
37 people.
ma'am, but very less number of, but most are from
Very
CSE.
few. Okay. So most of them are from CSE.
Yeah,
Okay.
exactly.
So are there people who are new to AI, ML?
No, ma'am, actually, in the previous days, they got talk on introduction to AI and some relevant
Okay.
topics. So they have some idea, brief idea. So you can
Okay.
directly proceed. Yeah.
Okay. Yeah. So slides I've taken from different places. Most of the slides are slide credits. So I'll just quickly go through like the basics of ML. So you all know what AI is and you all know what ML is. So basically ML focuses on learning from data and makes predictions on unseen data. So whatever is available, data is available, ML model will be trained, and finally that trained model will be used to predict new unseen data. So ML basics, most of the machine learning algorithms can be classified into supervised or unsupervised. Supervised means you tell the model that this is the data and this is going to be the label for the data. And from that, the model will learn, and then based on the learning, it will try to predict. Unsupervised, there is no label or no details about the data. The machine learning model will have to learn on its own based on similarity and then try to predict for unseen data or classify unseen data or group together unseen data. So usually when I tell my students, like I say, like the difference between supervised and unsupervised is like teaching a small kid to learn. So when we teach a small kid to differentiate between dogs and cats, then we'll keep on telling them, see, look at this, this is a dog, and it will learn it. When there is a cat, you tell it, see, this is a cat, and the kid will learn it. So this telling the kid that this is a dog or this is a cat is like having a label for the data. And when after some time, after some point in time, the kid will know that okay, this is the this is a dog or this is a cat, and then based on that, the kid would have learned well. But if nothing is being taught to someone, say we try to learn, try to differentiate between some animals, then what we'll say, we look at the features, then we'll understand, okay, this looks similar to this animal. So maybe both of these animals are similar or the same. Maybe this looks very different. So this could be a different kind of animal and so on. So that is unsupervised. There is no label or no one says this is this particular animal. Just looking at the animal, looking at the features, we try to understand it's a different one. So that is unsupervised data. So there are different types of supervised learning. I'm not getting into the details of those. You would have learned all these in your earlier sessions. Unsupervised learning, mainly there is clustering. Clustering, what is clustering basically? As I told you, unsupervised, you look at the data, try to group them together based on the similarity. So similarity measures are there. There are different techniques for finding similarity. Mostly it is based on a distance measure between the data, and points, data points that are very similar or they're very close to each other are put together into one group, and points that are farther away are kept in different groups. So clustering is a kind of unsupervised learning where similar kind of grouping is being done. So this k-means algorithm is one such clustering algorithm where when you have a number of data points, say you have a number of data points, you try to pick up, here there is d number of data points. You try to pick up only a few data points and call them as cluster centers or the centroids. And from each of these centroids, you try to find out how far every other data point is. So you take a new data point, you try to find out the distance of that data point from all the centroids, and to whichever centroid it is closer, you add it to the cluster associated with that particular centroid. So it is top. Then again you try to find the middle of that particular cluster you have formed, and then again try to recluster again till you reach convergence. So here just I've shown an example. There are some data points here, and you try to group them into two clusters. So you take maybe one point in one group and another point in another group and call them as the cluster centers, or you call them as the centroids, and then try to find out the distance of every other data point from this cluster center. And to whichever center the data point is closer to, you try to form a cluster. So first time, say this is the, say whichever is shown as plus is the chosen as the centroid, and these data points are closer to it, and you form a cluster. And this center, this cluster center, the centroid is chosen, and other points which are closer to this are formed in this group. Now we have two clusters at iteration 1. Then what we can do is we can recompute the centroids of these clusters. So when you recompute the centroids of this cluster, maybe you will find two other points now. So one for this cluster, this plus is the centroid now. And for this cluster, this plus is the centroid. And now again, you compute the distance from this newly found centroid with every other data point that is here. And you will get the distances, and you put the points put the points into the cluster to whichever it is closer to. So maybe in iteration 2, now we have formed two new clusters based on the distance from. So if you can see here, this point is closer to this cluster centroid compared to this centroid. So now this point will come in this cluster, which is associated with this centroid. So that's how it has become. So again, I can compute the centroids. So you'll get again yet another new centroids. Then again try to try to find the distance between this centroid with every other point here. And you will be able to get new centroids. But now here you find that it's again the same set of points. So we say that we have reached convergence. So here, this is an example of unsupervised learning. We were not told, or the machine learning model was not told about the label of each data point. Based on the similarity between the data points. The data points are grouped together into clusters. And how do you find the similarity? Usually it is by a distance function. Distance function can be calculated using, say, Euclidean distance. There are many other distances also. Euclidean distance is one such distance measure. But the weakness of this clustering algorithm is if there are outliers. Say if your data is looking something like this, there is one point which is farther away from the other data points. But when you're computing the centroid, maybe all these will form into one point, and this because the midpoint will fall somewhere here. And suppose if you remove off this outlier alone, then you'll have the clusters will look like what you see below. It will not look like what you see in the top A part. So when there are outliers, k-means may not perform well. Another issue is the selection of seeds, the initial seed value or the initial central points. So if the seeds are chosen differently, then it's possible that clusters can be formed differently. So in A, if you look at it naturally, it will look like you'll have a cluster in the left and another in the right. But if the seeds are chosen differently, it is possible that you get two clusters like this in the top and the bottom. So which doesn't look like a natural cluster. So this is a weakness of k-means. So if you use different seeds, you can find that the clusters will be formed like this and not like this. And k-means is not suitable for discovering clusters that are not looking like ellipse, okay, or looking like a spherical or ellipse kind of clusters. So that is not possible. And this is another algorithm, but I think I'll skip this off. So I want to move a little into deep learning models. I just want to know if deep learning was covered in an earlier class. Response. Okay.
And no,
Was
ma'am,
deep
it will be
learning-
from basic. It will be from
Pardon?
basic. No,
Pardon?
not
I don't
covered
get.
earlier. Not covered earlier.
Not covered. Okay.
Yeah.
Okay. Okay. So how I'll tell about deep learning. Okay. And then I'll move on to security issues in deep learning. Okay. Yeah. So if you look at before getting into deep learning, I'd like to talk a little about this perceptron. So perceptron was introduced in the 1940s, 1950s, where they tried to develop an artificial neuron very similar to the biological neuron. So it looks something like this. A single neuron looks something like this. Inputs X naught, these X's correspond to the inputs that are given to the neuron. So X naught, X1, X2, etc. up to Xn. And all these, each of these inputs are given weights, and you sum up all these weighted inputs, you find a weighted sum, and then you try to find out if this is greater than a threshold. If it's greater than a threshold, then you get a particular value, else you get another value. So here the thing is like, say for example, say students coming to college. So what motivates the students to come to college? So the output is the student coming to college or not. The input is the different factors that will motivate the student to come to college. And each of these factors will have different weights. Say, for example, attendance could be one reason, or it could be like the students like the courses that are taught on that particular day very much, or maybe they want to meet their friends, and so on. Some subjects are very interesting and so on. So there could be different factors. Those are the inputs that are contributing to this decision as to the student coming to college on that particular day. And each of these factors can be given different weights. So the input to the decision making will be a weighted sum. Say some can have weight of 1, some can have weight of 2, some can even have weight of 3, etc. and so on. It can even be zeros. Some weight can be very less, some weights can be very high. So you multiply this input with the weights and then add it up together, you will get the weighted sum. So it will be W0 X0 plus W1 X1, etc. up to Wn Xn. And get the weighted sum and then try to find out if the weighted sum is greater than a threshold. If it's greater than a threshold, then you say the output is positive. Else you say that the output is negative. This was the basic fundamental thing that was used in a perceptron. And later it is the same thing that is being used in deep neural networks. It was extended for deep neural networks. So here, if you're saying that it is greater than a threshold, it looks like you are using a step function. So if it's greater than, say, 0, if you're using step function, to be greater than 0, then you have positive value. If it's less than 0, then you have a negative value. Okay. Or you can even have any threshold here, and the threshold can be used. And later, rather than using a simple threshold, they try to bring in the artificial neuron, they try to bring in different activation functions. Because this input is linear because you just have a weighted sum. To make it non-linear, they try to bring in activation functions. So if you look at recent neural networks, there will be different activation functions like ReLU, rectified linear unit. You have TANH, and so on. There are different activation functions. So the perceptron, this is the algorithm for the perceptron. As I told you, find the weighted sum and you check if the weighted sum is greater than a threshold. If it's greater than a threshold, then the value output is 1. It will be -1 if the value is less than or equal to the threshold. So this perceptron can work as a linear separator. So if you look at this data, say if you have positives and negatives, if we use the perceptron, if you look perceptron, it will be like greater than, or it will be like having a linear separator. What do you mean by linear separator? It's just like drawing a line to separate between the two classes. If you look at this equation, you can see that this looks like y equal to mx plus c. Okay, y equal to mx plus c is the equation of a line. So this wx plus or minus a threshold is very similar to the equation of a line, and hence it can be looked at as a linear separator separating two different classes. Okay, so the decision boundary in a linear classifier is linear. If it's two-dimensional, it's just a line. And if you look at 3D, then it will be like having a plane. And in high dimensional space, you can say that a linear separator will be a hyperplane that separates the different classes. So here you can look at a linear classifier where you have an input image and these are weights, and here you have something called a bias. So what is this? So the input image here is represented as just 4 pixels. Usually, if you look at an image, representation of an image, the image will be represented as pixels, and those pixels will be put as a column vector. So here we have this input image, which is put as this column vector. And you can have a weight matrix to multiply this. And you can also have, instead of the threshold, very similar to the threshold, you can also have a bias value. So this is the basic thing that is being used in deep neural network between different layers. So the weight matrix between the different connections into the input vector plus the bias value will give you some information And then from that, you can apply an activation function to get some scores. So support vector machines also work based on having a linear boundary. So what happens here is that, say here you have two classes, okay, shown by circles and with square boxes. There are two input features, x1 and x2, and you try to plot these data points. And you can say that you can separate these boxes. So the two classes here are the boxes and the circles. And you can draw many lines to separate these two classes. So all the lines in this diagram, in this topmost diagram, separate the two classes very well. But which one is the best one? We need to find out a line that is far away from all the samples that are given here. Suppose if you take this line for separating, you can find that this line is very close to these two circles. Now, suppose a new sample comes and you're using this line as the model, SVM model, to separate these classes. Now, when it sees one new unseen example, what will happen? This, and it falls somewhere here. Say if there is a circle here, it will classify it as belonging to this class. It won't classify it as belonging to the class circle, because this is very close to this set of data points, the circles here. So how we will expect it should fall something like this in the middle between this dots, I mean circles and the squares. So the line that is farthest from all training examples will be a nice line, will be the best fitting line to separate the two different classes. Okay. And so first we need to find a boundary that will correctly classify. And then you try to find out the distance between the boundary and all the examples. The margin has to be separate. So look at this diagram here. The points that are close, the middle one should be the best line that separates the two classes. And the points that are close to this line are this circles here and this circle here, the red dots and this yellow dots. Now, you need to find this line. This is midway between these points and these points. Okay. So the distance between these points and the middle line is called the margin. So you should find the line such that this maximizes the margin. And these data points, the red points and these yellow points, these two yellow points and this one red point, which is closer to this middle line that separates, are called the support vectors, because only based on the position of this red point and these yellow points, we are separating the two different classes. So usually when you have linearly separable data, what do you mean by linearly separable data? In 2D, if you are able to separate the data with a line like this, or in 3D, if you are able to separate the data using a plane, then such kind of data is called linearly separable data. So if it's linearly separable data, then we can easily separate it using this linear classifier. But if we do not have linearly separable data, suppose if we have data as shown in B, the data that is shown in A is linearly separable. But the data that is shown in B is not linearly separable. So in the case of B, you can only draw a circle and separate the data. You cannot separate the data using a line. So this is non-linearly separable. So for non-linearly separable, you cannot use linear classifiers as the regular SVM, or you cannot use a logistic regression for classification. Then you need to be able to transform this data into linear space so that you can separate the data. So maybe you may even have to transform the data from 2D to 3D, or to a higher dimensional space, or to 4D, or to higher dimensional space, so that after that you can draw a hyperplane and separate the data. So when you have linear non-linearly separable data. You cannot use linear classifiers. So you need to change the data to another plane to separate the data. So here what is done is that here you have non-linearly separable data. Xn1 and Xn2 are plotted, and you have two classes here shown by the crosses and by the dots here, but you can only draw a circle to transform the data. So what is done is this is transformed, this input Xn1 and Xn2 are transformed to another space, another feature space, and then you try to separate the data. So here you can see that this dots and these blue dots and these red dots are non-linear separable when it is two-dimensional. But what is done is you move on to a different dimension, 3D space, and then you can use a plane to separate the data. So the original input space is mapped to a higher dimensional feature space, and then in that space you try to separate it linearly. For this transformation, transforming from one 2D space to maybe to a high dimensional space, you have different kernel functions. In the case of SVM, you have kernel functions like polynomial kernel, a radial basis function, etc., and so on. Okay. I think you know about this binary classification and multi-class classification, so I'm not getting into this. So now I want to get into this computer vision tasks because I'll be talking about security issues in computer vision tasks. So for ML, this computer vision has been one of the very primary areas of interest. And the main tasks that have been done in computer vision are classification, localization, object detection, and so on. Classification is given a particular image, the deep learning model or the machine learning model will say whether it belongs to a particular class or not. Okay, so if you want to do binary classification between cats and dogs, so given a cat image, it will say it is a cat and not a dog. Very similarly, given a dog, it will say whether it's a cat or a dog, whatever. So that is classification. Localization is like having a bounded box here. So given an image, if you want to find out what kind of objects are present in that, okay, maybe only the cat is here. So you need to put a bounding box around the object. It is called localization. And when you have multiple objects within the image, and if you're able to put bounding boxes around the different objects, then it is object detection. And very similarly, when you have multiple objects, you can also do semantic segmentation or instant segmentation. So in the case of object detection here, a rectangular box is put over each of the objects. Here, in case of semantic segmentation, we try to find out, take a particular pixel of the image and try to find out whether it is a part of this object or not. So you take a pixel here and you try to find out whether it's a part of this cat, this dog or not. Take an image here, try to find out whether it's a part of cat or not. Say maybe you take a point here, you'll try to find out whether it's a part of any of the objects here, else you just leave it. So that will give you like a border kind of a thing, segmentation for this, for the objects that are present. So this is especially useful maybe in automotive sector when you're trying to do instant segmentation of maybe trees, the pedestrians, the road, etc., and so on. So ML, the conventional ML and DL are different. So deep learning, you can see that in the case of ML, usually image tasks for computer vision tasks, you will extract the features from the image and then you try to give to a model, ML model, and you will get the output. So this is the case for the conventional ML models that were used earlier. say you can use any kind of classifier, maybe decision trees, etc., and so on. In all those cases, you need to extract the features from the image and give to the ML model. But in the case of DL model, it's not the case. You give the input to the model by itself will extract the features and do the classification and give you the output. Say if you're using a CNN, so convolutional neural networks, which have been primarily used for image related tasks or computer vision related tasks, the CNN by itself will extract features from the input, and it will learn the features from the input, and it can classify on its own. And DL applies. What happens with DL is that, so given this particular image, and if you want to try to find out maybe object detection or something like that, so it will extract the low level features. There'll be multiple layers in the deep neural network, and each of these layers will do different tasks. So the initial layers will try to extract low level features, and then the later layers will try to extract higher level features, and then these features will be given to a classifier, maybe a softmax, and then you'll get the resultant. So DL works layer after layer. So the resultant will get more clearer, or the results will get more clearer as we move away from the initial layers, as we move towards the final layers of the deep neural network model. And many different DL models were proposed, and they found that in many cases, they found that deeper the model, they get better classification accuracy. So DL provides a framework for learning in the supervised as well as unsupervised manner. Not only for computer vision techniques, you all know that it is being used for text, and in recent times, there are a lot of generative AI models which can generate new images as well as text, and DL models can work with text as input, video as input, images as input, and it can also even take multimodal data, different modes of data, and then work on it and provide you with different results. So neural networks, here just showing this MNIST data set. Have you worked with, is there anyone who has worked with the MNIST data set, or you're quite familiar with the MNIST data set? No idea. No answers. Okay.
I have worked with it.
Okay. Okay, fine. I'll just continue. Yeah. So this MNIST data set has got handwritten digits from 0 to 9, and it was basically to recognize handwritten digits. And this data set provides these digits, and you can develop models that can recognize, develop models that will be capable of recognizing handwritten digits. So usually when you look at any image that is given, when it is given as input to a deep learning model, the input will go like this. You'll have the intensity of each pixel of the image that is given as input to the neural network. Suppose this is a 16 cross 16 image, then you'll have 256 different values here. And suppose if it's a gray level image, then you'll have 256 intensity values, and each of these intensity values should be given as input to the neural network. So here 16 cross 16 is 256, and there will be 256 inputs that are given to this neural network. Say this is the input as even input to the neural network. So here we are just assuming that if there is an ink, then the value of the pixel is 1, And if there is no ink, the value of the pixel is 0. And what will be the output? The output will be a digit between 0 to 9. Because it needs to recognize, the neural network needs to recognize whether the input is 0, 1, 2, or 9. And each of these values, say y1 may correspond to 1, y2 may correspond to 2, etc. and y10 may correspond to 0. So this each of these, each dimension here will represent the confidence of a digit. Okay. And the output is, suppose you get an output like this, 0.1 for this y1, 0.7 for y2, etc. and 0.2 for y10. Then it means that it is assuming, the neural network is saying that the input is 1 with a 0.1 confidence, with a 10% confidence. And it is saying that the input is 2 with a 70% confidence. It is also saying that the input is 0 with a 20% confidence. For all the other ones, it is saying, it is giving a 0 assume, saying that it is not assuming that it could be 3 or 4 or 5, etc. up to 9. So this kind of outputs can be got out of the neural network. So here the maximum value is for this input 2. So we can say that the neural network is saying that the input is the digit 2. Okay, even though it has given some value for 1 and for 0, it is giving the maximum confidence for this input 2, for the digit 2. So we can say that the neural network is classifying this as 2. So what I'm trying to say here is that inputs are given as pixel values in the case of image to the input layer. The outputs can be taken as probabilities. Maybe you can use a softmax classification layer at the end. The output can be taken as probabilities. So in between, you will have the neural network. So the image given to the input layer, and this input layer, and this neural network, in this input is given to the neural network. The neural network will give the output between y1 to y10, which is a probability, which are probability values. And what does this neural network do? It is mapping this set of real numbers. Okay, from 1, you'll have 256 different values here corresponding to each pixel in this input image. It will take this vector and convert it into another vector with 10 values, 10 real numbers. So how does this do? That is what happens in between in this neural network. So the neural network can be looked at here as a function that maps real numbers, 256 real numbers to 10 real numbers. Okay. So neural network consists of a lot of hidden layers with neurons, and these neurons are very similar to whatever I told earlier. Okay. So you'll have this input, say you have inputs A1 etc. up to AK, and you need to find the weighted sum of all these inputs. Each of these connections from the input neurons will be given a weight. So the connection that comes from A1 will be given weight W1, from A2 can be given weight W2, etc. From AK it can be given weight WK. So now you find the weighted sum, you'll get A1W1 plus A2W2, etc. up to AKWK. And you can also have a bias value that is added to in this neuron. So you sum up all together, you will get the input that goes into the neuron. Now this input value, you will apply an activation function on it and you will get the output. So A1W1 plus A2W2, etc. up to AKWK plus the bias, you get this Z. And on the Z, you apply an activation function sigma to get the output of the neuron. So what does this neuron do? It maps the set of inputs onto an output number. So here you have k real numbers and you map it onto a single real number here. So this neuron maps k real numbers to a single real number. And this is one neuron in one layer of the neural network. You will have many such neurons in different layers of the neural network. So each layer can have a number of neurons, and you can have many layers also in the neural network. So your neural network can look something like this. This is an example of a neural network. You can have the input, you can have a hidden layer, you can have an output layer. So this is a very simple neural network with just one input layer, output layer, and one hidden layer. That's all. Okay. And there are interconnections. There are connections that connect the input layer to the hidden layer and connections that connect the hidden layer to the output layer. And you can find that these rounds or these circles in each of these layers correspond to neurons. So here in the input layer, there are 3 neurons. And in this hidden layer, there are 4 neurons. And in the output layer, you have two neurons. And these are called dense connection because from one neuron here, you have a connection to every other neuron in the next layer. So if you look at the first neuron here in the input layer, it is connected to all the neurons in the next layer, to the first neuron, second neuron, third neuron, and fourth neuron. Very similarly, all these neurons. And from the hidden layer also, those are connected to all the neurons in the output layer. Okay, so these connections are called dense connections. And now, when you look at the input layer, in each of these connections will have some weights associated with it, and there will be a bias value that can be connected to the neurons, to each of the neurons. And then so what will be the input that goes to each of the neurons here? It will be the weighted sum of whatever comes inside plus the bias. And then you can apply an activation function which goes out of the neurons. Okay, so if you look at this neural network, initially when you're training a neural network with data, maybe you'll take one, maybe simplifiedly if you're saying, you can take one data point, and that data point can be given as input to the neural network. And there will be some weights in each of these interconnection and bias values to each of the neurons. All these will be initialized to some random value initially. And then once you give this input to this neural network, you will get the output for that particular input sample. And the output may be correct or may not be correct. If the output is not correct, then you'll have to change the weights and the bias values. And then you'll have to check again with the next data sample and so on. So how does training happen? If you have, say, 100 dog images and 100 cat images, and if you want to classify between dogs and cats. So these 100 dog images and 100 cat images, these 200 images will have to be given as input to this neural network one by one, or you can even give in batches. And you need to find out if the neural network is classifying all the 100 cat images and the dog images correctly. If it's not classifying correctly, then you need to find out the loss. That is, you need to find out how different the output is generated by the neural network compared to the actual output. The probability values, you can find a difference and you can calculate the loss. So you need to calculate the loss for all these 100 cat images and 100 dog images. For the 200 images, you will have some loss value. Now this loss value you need to find the gradient of the loss value and propagate it back into the neural network. And you need to update the weights and the biases. Okay, so weights and the biases will have to be updated. And the next time, what you can do is that with the new set of weights and biases, again give the 100 dog images and the 100 cat images, then again try to find out what the loss is with the new set of updated weights and biases. So these are called epochs. So the first epoch, you'll send the data samples and find the loss. Then again, second epoch also, you'll send the data and find the loss, and so on. So this can continue till your loss reduces to a minimum level, or maybe the loss is not reducing, the neural network is no more learning, and so on. So what do you mean by learning here? The learning is like updating the weights and biases of the neural network. So updation of weights and biases is called, if it's called learning, then how many learnable parameters are there in this particular neural network? So here you can see that there are 4 neurons in the hidden layers and two neurons in the output layers. And you look at these interconnections. Here you will have 2 into 4, that is 8 interconnections will be there in the layer in between the hidden layer and the output layer. And between the input layer and the hidden layer, you will have like 3 into 4, that is 12 interconnections. So in each of these 12 interconnections, there will be weights. And similarly, in each of these 8 interconnections, there will be weights. So, and it will be like 20 weights. And there will be a bias that can be connected to each of these neurons. So to each of these neurons, it will have a bias, and each of the neurons here also you will have bias. So it will be like 6 biases. Totally there will be 26. Put together there will be 20 weights and 6 biases. There will be 26 learnable parameters. And so these weights in the layer between the input and the hidden layer can be represented using a matrix if you want. Similarly, the one between hidden and output also can be represented using a matrix. So in general, deep neural networks will not have only one hidden layer. They can have many hidden layers. So many fully connected dense layers can be there. And this is also called a multi-layer perceptron. So each neuron in one layer is connected to all the neurons in the succeeding layers. We can look at a small example of how weights are calculated, the weights and biases are calculated, or how data flows through the neural network. Say the input is 1 and -1, and you have 2 neurons here. And this first value goes from here to this first neuron, and this -1 goes to this first neuron. And the weight here is 1 and -2. So the input to this neuron here is 1 into 1 plus -1 into -2. So you'll get 1 into 1 plus -1 into -2 plus this 1 is a bias value. So it is 2 plus 1 plus 1. It is 4. That is the input that goes into this particular neuron. And suppose if you're using a sigmoid here as the activation function, sigmoid is represented as 1 by 1 plus e power minus z. So here 4, so 1 by 1 plus e power minus 4 should be calculated, that is 0.98. So 0.98 will be the output that comes out of this particular neuron. And you take this second neuron, the input is -1, and the weights associated are -1 and +1. So here you can see that 1 into -1 is -1, -1 into 1 is -1. So -1, -1, -2. So it is, the bias is 0, so it is -2. So -1, -1 plus 0 is -2. And you apply the sigmoid, you'll get 0.12. So this is how data will flow in the neural network. And this is called the forward pass of the neural network. So as we saw in the earlier slide, you have 2 neurons in the first hidden layer, and you get 0.98 and 0.12 as output. And again, the second, you have another hidden layer here. You have weights associated with each of the interconnections, and you find the weighted sum along with the bias, apply sigmoid, you'll get an output of 0.86 for this neuron and 0.1 for this neuron. And very similarly, you have another layer, again, weights for the interconnections, and you'll get the output as this if you're using sigmoid. And what you can see is that this neural network has mapped these two inputs, 1 and -1, as 0.62 and 0.83 in the output. So we can use even matrix operations for this. So here you can see that the weights can be represented as a matrix 1, -2, and -1, 1. And the input also can be represented as a vector, and the bias can be represented as a vector 1, 0, and you can apply a sigmoid and you get a vector as resultant. So this is very useful when you're implementing this, and this can be represented as sigma of wx plus b. So as I told you, the same weighted sum plus bias which was used earlier is still used as still used in deep learning, deep neural network as well. The only thing is you find a weighted sum plus the bias, and then you apply a sigmoid over that to get the resultant. So when it is multiple layers, then what happens? Again, weight matrix into the input plus the bias. So this happens for different layers. First layer, second layer, the nth layer, and you get the resultant. Okay. So a multi-layer neural network maps the inputs to outputs. So it basically, you can look at it as performing a function. So first is you have W1x plus B1, then a sigmoid over it. That will be the output of the first layer. And then W2 into the output of the first layer plus the bias. Again, sigmoid over it. It will be the output of the second layer, and so on. Then you apply the weight matrix of the nth layer onto the output from the previous layer plus the bias. Again, you apply a sigmoid, you'll get resultant. So when it is multi-class classification, the output layer is usually a softmax layer, or softmax activation function is employed. And usually, if it is binary, the softmax can boil down to to a sigmoid activation function. And but if it's multi-class, it's easier to use softmax layer. So how does a softmax layer usually work? Okay, so this blue box can be looked at as the softmax layer. They have inputs that go to the softmax layer represented as Z1, Z2, and Z3. And the output is represented here as Y1, Y2, and Y3. So Y1 is e power Z1 by e power Z1 plus e power Z2 plus e power Z3. And Y2 output, second output is e power Z2, which is the second input, by the sum of the three, e power Z1 plus e power Z2 plus e power Z3. That is, you normalize it. And then Y3 e power Z3 by e power Z1 plus e power Z2 plus e power Z3. And you get some probability values in the range 0 to 1. And you can find that the sum of these three probability values will be equal to 1. So it is like getting the highest, the best output will get the highest probability value. So an example is shown with inputs. If Z1 was 3, Z2 was 1, and Z3 was -3, then what would be the output values? So if this is the case, then the Y1 is 0.8 and Y2 is 0.12 and Y3 is 0. And these different probability values show that the highest probability is with this Y1. So the best output should correspond to the output Y1. And why do we have this activation function? Here we saw that we used sigmoid in the different layers as activation functions. And final layer we use softmax, even sigmoid can be used. And why do we use activation function? To basically understand non-linear data representation. So these activation functions make the data to be non-linear. Otherwise, without the activation function, it would be just a linear function. So because you have weights into the input, then again plus a bias, again it will be like weights into the input and so on. It will be like a linear W into X. So only when you have these activation functions, you can understand more complex information, more complex data, and that's why we have non-linear activation functions. So there are a number of non-linear activation functions. I'm not getting into the details. Sigmoid, tanh, ReLU, leaky ReLU, all these are activation functions. Now, what is meant by training neural network? As I told you earlier, the neural networks, the weights, matrices, and the bias vectors from all the layers should be trained. Should be trained so that the neural network performs the data that it wants to perform. Suppose if the data here is like okay. So training is to learn a set of parameters, the weights and the biases, such that it is optimal. And but getting the best optimal weights and biases is a big problem. We are not able to get deep learning neural networks which will give you 100% accuracy for the entire set of test data that is given. Maybe for one particular set of data, it can give very good accuracy, but it may not give you very good accuracy when it looks at some other set of data. So 100% accuracy for all data, I don't think it is possible with neural networks as of now. So how training happens is you will have some loss function, and the loss function is nothing but trying to find out the difference between the prediction of the model and the true label of the model. So here, say this is the input. It looks like 1, and the output the model gives is it gives for 1 it gives 20% accuracy, for 2 it gives 30% accuracy, and for 0 it gives 50% accuracy. And it says that it is 1. It assumes that it could be 1 with a 20% probability and so on. But it is the input is 1. So the output should have been probability equal to 1 for Y1, and the other should have been 0, because the true label is 1. The input is actually 1. So now what we need to do is that we need to find out the loss. So how is loss found? Loss is found using mean squared error or by other modules, mean absolute error, cross entropy loss, etc. and so on. Basically, you try to find out the difference between the true label and the actual label that is got. Actual model's prediction and the true label. So here, Y1 should have been 1. So you try to find the difference between this 1 and 0.2. That is a difference value. And very similarly for y2, it should have been 0 and 0.3. There's a difference. So if I try to find out all these differences, apply some loss function onto it, you calculate the loss. And this loss should be propagated back into the network using algorithms like back propagation, and the weights and the biases should be updated. So when you have many number of inputs like this, for each of the inputs, you can calculate the losses. And when you have n such inputs, for all that, you can calculate the losses, and the total loss will be calculated as a sum of the individual losses corresponding to each number. And this total loss will have to be reduced. How do you want the loss to be? The total loss should become 0. So you try to reduce the loss and bring down the loss to 0. So there are many loss functions again. For classification tasks, you have a set of loss functions. For regression tasks, you have a set of loss functions. Say for neural networks like autoencoders and restricted Boltzmann machines, you have another set of loss functions and so on. So classification tasks, you can use cross entropy, you can use for regression task, you can use mean squared error or mean absolute error. And you can use scale divergence for autoencoders and so on. So there are different types of losses that can be calculated. And then what do you do with this loss? You try to optimize the loss function, or you need to reduce the loss function. So for that, what you do is you try to find out the gradient of the loss. What do you mean by gradient of the loss? How the first order derivative, how the loss varies with respect to the different parameters. So here the parameters are the weights and the biases. So you try to find out the gradient of the loss with respect to the weights and the parameters. And then based on that, you try to update the parameters, which are the weights and the parameters. And this is done, and we can use a gradient descent algorithm for updating the weights and the parameters. So it can be like the new parameter can be the old parameter minus a learning rate into the gradient of the loss with respect to the parameter. So theta nu, if theta is the parameter, theta nu is theta old minus alpha which is the learning rate, into dou L by dou theta, which is the gradient of the loss. Okay, so I think like with this, I'll move on to security. I will not get into the details of more details of deep learning model. So all these deep learning models, we see that deep learning models are used for various purposes, and are all these deep learning models really secure? Or do these deep learning models prone to attacks? Do these have security issues? And there are a number of security issues with deep learning models, or many attacks can happen even on deep learning models. These attacks can happen before the training of the model, or even during the training of the model, or there can be attacks even after the machine learning model has been trained. So this is one type of attack which is called adversarial attack, which is very prominent on deep learning models as well as on machine learning models. So here in this example, in this diagram, you can see that there is a deep neural network which has been trained to classify images, different types of images. And this neural network has classified a lion as lion correctly with a confidence of 99%. And given this race car as input, it has classified this race car as input correctly, again with the classification accuracy of 74%, or with the confidence of 74%. And this light, it is classified with the confidence of 99%. And all these three images, it is classified correctly. But now, when these input images are manipulated adversarially. So what do you mean by adversarially manipulating the image? The input image will be perturbed a little, will be changed a little, or perturbations can be added to these input image slightly, but these perturbations will be such that the changes are not seen to the human eye, or the perturbations will not be seen to the human eye, or those will be imperceptible perturbations. So when you have such kind of perturbations done to this input image, the deep neural network gets fooled. So here you can see that this line image looks like a line image only to us, but it has been perturbed a little, and it's the same neural network as we had earlier. So this same neural network is used, the same trained neural network, and this perturbed line image is now classified as pelican with a 97% probability. And this car image is race car image is classified now as a speedboat with a 97% accuracy. And this traffic light is classified as jeans with a 97% accuracy. So this is from this famous paper, ICLA 2014 paper by Zegri et al. And what for us, to the human eye, these images don't look like manipulated images, don't look like compromised images. So if you see the difference between the original and the adversarially manipulated images, you can see that the difference is very small. This is the original image and this is the attack image. And the difference between this original image and the attack image is only this. You can see that there are few white dots here and there. And very similarly, the difference between these two car images is only this. And the difference is very less. The attack is imperceptible, the changes are imperceptible, but they fool the deep neural network a lot. So this is a big security risk for deep neural networks. And small perturbations can make the network to misclassify an image. And these perturbation can be very imperceptible, will not be perceptible, cannot be seen by the human eye. And in addition, say you have a neural network that is trained on a different subset of data sets, and you use the same perturbation, and this same perturbation can cause a different network that was even trained on a different subset of the data set to misclassify this particular input. So that is also possible. And this is again another example. This is called adversarial machine learning, and this is another example where adversarial examples are given as input to the ML models. And here the panda, which was classified as panda correctly with a 57.7 confidence, by adding a small adversarial noise, it is classified now as gibbon with a 99% accuracy, but the gibbon actually looks like this. And here in this example, a school bus, by adding a few small perturbation, this is actually scaled up for better visualization, and that is classified as ostrich. And if there is a stop sign, if you add a small adversarial noise to this stop image, and if it is not recognized by a self-driving car, then the car can keep going. It can result in an accident. And people also try to see if small patches added to an image, if that will cause a deep learning model to fail. So here what they have done is, in the lab test, they try to put some small black and white patches and some letters along with the stop symbol. And they found that the stop sign was understood as a speed limit sign. So it just slowed down and just the vehicle kept moving. And even in the field test, they found that the stop sign was misunderstood by automatic or self-driving cars, and it was like misclassifying it as a speed limit 45 sign. So in lab test, they found that it was 100% attack, the 100% success on the there was 100% success, and in the field test there was a 85% success. And then this is another example where a 3D printed turtle is misclassified by a deep neural network as a rifle, and it was classified as more than 90%, with more than 90% accuracy as a rifle. So the texture of the turtle is designed to mislead the deep neural network. And it is also possible that a person cannot be detected if he just having a hoodie, or if he is carrying some, he's holding a placard, or he's wearing some image, he's wearing an adversarial patch, and then in that case the person can go undetected by cameras, and intruders can get past security cameras with this. So it is also possible. And here in this case you see that in the original image, it's the original image, and correctly it is saying it is doing instant segmentation or semantic segmentation of people who are crossing, but of pedestrians. But in the second adversarial example, for us, it is not, it is clear, it looks very correctly, but the ML model is full. The self-driving car says that there is no pedestrians in that. So this is an issue. And there can be this kind of evasion attacks in the physical world also, wrongly people getting classified as other people by just wearing maybe some specs. It can get classified. Here there is some perturbation that is added, and this image is classified as another image. Again, here a perturbation is added, image is classified as other image, and with just a specs it is classified as other image, and so on. And here again you have specs that have been used to classify as somebody else. And again, here signals as stop sign, signages are understood differently by deep learning models. Again, signages being understood differently by deep learning models, and so on. So you can see that the classification accuracy of deep neural networks, when there are adversarial images, stops very significant. It drops very low to a very low level when compared to the non-perturbed images. So here some examples are given. When there is no attack on the MNIST data set, it gives a classification accuracy of 99.4%. And on CIFAR, maybe the model gives an accuracy of 94.8%. And on the ImageNet dataset, gives a classification accuracy of 74.5%. But the classification accuracy on adversarial images, say FGSM, created by different adversarial attack methods. These methods, FGSM, fast gradient sign method, projected gradient descent, deep fool, and CNW, all these are different attack methods. After these attacks, after creating adversarially perturbed images, adversarial images or perturbed images, the data sets, the neural network failed, or the neural network produced very poor accuracy for the different data sets. So when there are no perturbed images, while it gave 99.4% for the MNIST data set, it gives only 54%, 9%, even 0% for some attacks for the MNIST data sets. Very similarly, you can see that even for CIFAR and the ImageNet data set, performance is very poor. And ML basically, it has limited capabilities to reason about even spatial relations of the objects in the images. even if you just mix up together pixels and if you have a jigsaw kind of a puzzle kind, then even then it is possible for the DL models to understand. Okay, and that is also possible. So very similar to how visual system can be fooled, even deep neural networks can be fooled. And even abusive use of ML is on the rise. People generate fake content, also known as fake videos, deep fake images, and these can be used to fool people. And cons can be used to generate fake images which look very similar to real images. So generative adversarial networks, and there are quite a lot of different types of generative adversarial networks, which can different types for generating different types of images. And now recently even you have different generative transformers, etc., and so on, which can be used for generating stuff. So there is also possibility of abusive use of ML. So this adversarial machine learning is this area of machine learning which learns about adversarial attacks and defenses against adversarial attacks. So there are a lot of different types of adversarial attacks, and there are different types of adversarial attacks and different types of defenses. And these adversarial attacks are not only against deep neural networks, it can also be created against even the regular machine learning models. Even regular machine learning models are vulnerable to these kind of attacks. And not only image data, there are a lot of work which have told that even other data formats are vulnerable to attacks, these type of attacks. So even audio data, text data, malware files, spam messages, or even sensory data, any kind of data are prone to adversarial attacks. So, but initially when this came up, only in the image domain, predominant work was done for adversarial machine learning. And the common data sets that they had been used for evaluation in adversarial machine learning, or this MNIST data set, which has got 60,000 images of digits 0 to 9, and or the CIFAR-10 data set where they have 10 classes. They try to give images of 10 classes and 6,000 images in each class: cars, birds, airplanes, etc., and so on. Totally put together, there are 60,000 images in CIFAR-10. And ImageNet is another famous data set that is used. And ImageNet has got 14 million images with 20,000 classes. And ImageNet 1K is one subset where there are just 1,000 classes, and totally there are 1.28 million images. And recently, a lot of focus has happened even on large attacks on large language models. And so I just try to give a small detail about the different adversarial attacks. Adversarial attacks can be classified based on the goal of the adversary as a poisoning attack, or evasion attack, or privacy attack, or availability attack. So in the first case, it will cause the machine learning model to perform incorrectly. Okay, so once it is trained, you try to give some samples such that the model will not perform correctly, it will give you wrong results. The second is privacy attack is, it will try to find out what kind of training data or what kind of training model was used to acquire, will try to get knowledge about that. try to get knowledge about the training data or the model. So which is loss of privacy. That should not happen. The other is making the model itself to be to become unavailable. So this is one kind of based on the adversary's goal. The second is based on adversary's knowledge, what the adversary knows, we can divide this model into white box. We can divide the attack into white box attack, black box, and gray box attack. You can call it a white box attack when the adversary or the attacker knows fully about the deep learning model, the structure. It knows about the number of neurons or the number of layers, or it knows about what kind of weights are being used. It knows about what activation function is used, hyperparameters like activation function, the learning rate, and what kind of loss function is used. So if all these parameters and hyperparameters are known, then that attacker can interact with the model and he can create adversarial input. So there are different models, white box attacks that have been created by different researchers like FGSM, MIFGSM, etc. and so on. And then you have this black box attack. The black box attack has the adversary or the attacker does not know anything about that model. He or she does not know how many parameters are used, or what are the number of parameters available, or how many layers are used, or what kind of learning rate is used, what kind of activation functions are used. Nothing is known about the model or the architecture of the model. Only they know that there is one model which is a black box model. So what they do, they try to give input to the model and try to get what output that model is giving. So they will now know for this input, this is the output that the model is generating, or for this input, this is the label that the model is generating. With this information, they'll try to create one new model, a new substitute model. So for this new substitute model, they'll train the data with the input and output combination that they have got from the original model. So from the original model, given an input, they know the label. Now they'll have created a data set with input and the label. And with this data set, they'll try to train a new model. So now they'll be able to create a new model which does the same work as the original model. And now with this new model that they have created, this substitute model they'll created, they will create attacks in the black box method and transfer those examples to the old model, to the original model. So black box attacks are actually realistic because usually the attacker will not have provision to the network architecture and different hyperparameters of the model. Now with this, they can find or they can craft a nearly similar model that is very similar to the original model. And then gray box attack. In gray box attack, they have some knowledge about the ML model, and based on that, the attacker can create create adversarial samples. And based on the attacker's target strategy also, there are different types of attacks that are possible. One is targeted attack. In this, the attacker will cause the ML model to produce a particular target label for an input. So given an input, it will be like the output should be this particular output. Okay. Not only just looking at getting an incorrect output. It is also like getting getting a particular output. Okay. But in the case of non-targeted attack, given an input, the attacker just wants the output to be an incorrect output. It doesn't bother about what kind of output is got. Only the output got should be an incorrect output, and not worried about what type of output is got finally. Okay. So if the input is given like as a lion, a perturbed lion, then it wants the output to be something else other than the lion, not a particular class. In the earlier case, say you can put up the attacker may want to put up the stop sign, and it should certainly predict as the output should be certainly predicted as speed limit 45 sign. So attackers target strategy, based on the attacker's target strategy also, the type of attack can change. So basically, the attacker, the ability should have the ability to influence the model. And can the attacker influence the initial training data or model? And this is one question that needs to be worried about, initial training data model, if it's available to the attacker, then he can modify that also. If that is not available, then from the model, he try to give samples and make the model misbehave. So evasion attacks. Evasion So evasion attacks is a type of attacks that arise due to adversarial input introduced in the models, and attacker tries to so attacker will try to cause a misclassification. He'll try to identify the key set of features and to modify for the evasion. And again, as I told you, the strategy depends on the knowledge of the classifier, what algorithm, the feature space, training data, etc. are being used. So this is evasion attack. Only 10 more minutes I have. So these evasion attack usually happens only on the testing phase. They can't tamper with the machine learning model, but they can cause the machine learning model to behave wrongly, misclassify inputs, and so on. And this can be used to bypass a detection system. Say if there is a face recognition system, this can be used to bypass a face recognition system. And this is more common than the poisoning attack. Poisoning attack is poisoning the data or poisoning the input training data so that the model gets trained wrongly. But here we are not doing anything with the trained model, but we are making the model to misbehave, and that is called evasion attack. And the very common evasion attacks or adversarial attacks that have been used are this FGSM, PGD, DFool, CNW, etc., and so on. And it is also possible to have a random noise attack. Like the simplest form of this adversarial attack is to add random noise to the input image, and it will wrongly classify. So here you can see that the gorilla image is added with some noise, random noise. It's not even generated using an attack type of specific type of attack, and it is wrongly predicted. That is also possible. So for the past few years, many people have worked on this, and many researchers have developed a lot of attacks in the white box category, black box category, and poisoning category, and so on. So the next few minutes, I'd like to concentrate on this attacks which are possible on large language models also. So this is this paper in 2023, we came in 2023, called this universal attack on large language models and transferable adversarial attacks on aligned language models and so on. So here what is done is that usually when you give an input prompt to large language models to generate outputs to questions that large language models would normally refuse to answer, then see, for some kind of inputs, the LLMs will not generate outputs. They would say you're not supposed to answer and so on. But when adversarial prompt is added, or when adversarial suffix is added to the prompt, the original prompt, then LLMs can produce answers that are objectionable or offensive. So the left side, there are a few prompts that are given, and if you add adversarial suffix to these prompts, it'll give you answers which usually it does not give. And this universal attack was applied to several LLMs like OpenAI, ChatGPT, Claude, Bard, etc., and so on. And they found that um, all of these LLMs were fooled or cheated by this particular type of having adversarial prompt. So on the whole, what is currently needed is the need for a trustworthy AI. So we use AI and we use AI models for different kinds of purposes, and we say that AI is going to change our lives. We say that AI is going to make life simpler, and we say that AI is going to be used in all walks of life, in different industry applications, and so on. But in spite of all this, AI models are prone to attacks, and hence, how do we trust AI models? Especially, say, if you're going to use AI models for, say, the industry or healthcare, where things are very sensitive, maybe self-driving cars, autonomous vehicles, and so on. Here, when you're using AI, it's going to be very sensitive to use AI unless it is trustworthy. So, trustworthy AI should be robust. Even small input perturbations causing an impact in model predictions is not good. So robustness is very important for trustworthy AI, and it should be explainable. So most of the decision making process of our models is non-transparent. We really don't know what is happening inside. Why AI gave such a kind of a prediction, we don't know. That has to be made transparent, and that has to be made easier to understand. Whenever the AI gives a decision as the final decision, we should know that why this decision is being made by AI, and only then users can trust it. So now the working of the AI model also should be transparent. Only then we can trust the AI very well. And then generalization is also very important. Say you are training a particular AI with images from one hospital. It may not perform well with images on another hospital. Maybe because of the lighting, because of the setting of the equipment, because of the person who is using the equipment, etc., and so on. So that should not happen. So it should be generalizable. Any AI model should be generalizable. Only then it will be trustworthy. And AI models should not show bias. Say it is more modeled or it is trained on one particular kind of data, say maybe on male subjects, then it should perform well on female subjects also. Okay, there should not be gender bias. There should not be bias based on race or culture. There should not be bias based on age. Say models are trained on small people should work on old people also. When old people are images or maybe other data give us an input. So, and maybe if it is trained on people of a particular race, then it should work on people on other race also, which is very difficult. So fairness is another issue which has to be looked at when AI models are being used. Then another important data is that when you're using AI models, when you're using some data for training the AI models, they should not be by any means the data that is used for training the models. By any chance, it should not be known to the users of the model. If by some means the users of the model are able to get some data on which the AI model is trained on, then it results in privacy breach, which should not be there. So sensitive privacy, private information which is used for training the model should not be revealed, should not be told outside. And then it should also align with the domain knowledge. Usually, when you're talking about trustworthy AI, say if a doctor looks at a particular image and tries to classify the image, the same kind of knowledge should be there for the AI also. It should not uh, think something and say something. So recent times people talk about hallucinations of large language models. So if large language models look at just patterns and put together information, give wrong information, wrong text, then what to do? It may look very correctly, grammatically correct, but is the content correct? Can we trust? So will large language models give some reasoning for why they have given such a kind of an output? Then maybe to an extent we can trust the information that comes out of large language models. And ethical issues. The model should produce ethical decisions that are aligned with human values also. It can't give decisions which are not aligned with human values. That is also very important. So trustworthiness of AI is very important. It's a very necessary topic or necessary research area in which people can work uh, in the future, because AI is going to be there, AI is going to impact lives, but AI also should be trustworthy. And as I talked to you about different attacks, these attacks, there are also a lot of different types of defenses that are possible for these attacks. And I'm not getting into details about all these defense mechanisms. For the evasion attacks that I talked about, adversarial training is a particular type of defense mechanism in which adversarial samples, we generate some adversarial samples, and the AI model can be trained with such kind of samples also. And we can also have different mechanism with which you try to detect the adversarial sample before giving it as input to the neural network. Maybe can do some kind of filtering to the input. Some papers have worked on using Gaussian filters on the input and then giving it as input to the neural network. And some had worked on regularization also, regularization on the neurons, on the number of neurons, and applying different regularization functions and trying to see whether it can act as a defense against evasion attacks. And gradient masking, obfuscation are also being used. So there are different defense strategies, and quite a lot of people have worked on that. This is one set of defense strategies which are being used by different people to work against adversarial attacks. So with this, I think I'd like to conclude my topic. If there are questions, I'd like to take a few questions.
Ma'am, there are some questions in the chat box.
Okay, I'll look at it.
I'll interpret them to you.
Okay,
so first question is usefulness of gradient descent.
Okay, gradient descent is used for back propagation. It's basically to decide like how much of the weights you should, how you should vary the weights. Are you going to increase it a lot or going to decrease it a lot, depending on how the losses vary. We can talk about like the gradient descent algorithm for a longer time if you want, but
okay, ma'am. The next question is this type of attacks is applied in digital image processing? If yes, how?
and what do they mean by digital image processing? Anyone who was asking the question, like if they can ask, then it's like, see, these attacks are possible on images. Okay, any neural network, if it is going to, say you have a neural network which is going to do some image kind of processing, okay, say classification based on the input image, or a neural network that is going to even generate images. Any kind of task a neural network can do on input images. These kind of attacks are possible.
Ma'am, next question is, can you tell or throw light on the RNN and its reliability?
Recurrent neural networks and its reliability. Okay. And reliability based on adversarial attacks or what?
Ma'am, they have not
No,
said
nothing
that
is mentioned. Okay.
as your preference. Yeah.
Okay. Okay. See, recurrent neural networks are, see, if you look at these large language models are based on transformers, and you can say that they are an extension of recurrent neurons. Recurrent neural networks are used for manipulating sequences. Okay, say text. And later they came up with LSTMs, GRUs, and so on. So these adversarial attacks are possible on any kind of neural network, all possible types of neural networks.
Anyone, if you have any questions, you can unmute yourself or put your questions in the chat box.
But primarily adversarial attacks were first found out only for convolutional neural network for images as input, for CNNs. But recently they are looking at even vision transformers are prone to adv attacks. LLMs are prone to adv attacks.
Okay, thanks, ma'am. I guess there are no more questions.
Okay.
Yeah, there are no more questions. Okay, so as we come to this insightful session, I take this opportunity to express my heartfelt gratitude to you, ma'am, for sharing your valuable knowledge on artificial intelligence and machine learning and cybersecurity related information. Your expertise and insights into the future of artificial intelligence and cybersecurity like really helped us all and enlightened us. Thank you so much, ma'am, for attending today's session and like providing us with all the knowledge. I hope we collaborate with you again in the future. Thank you so much, ma'am.
Yeah, thank you. I'm glad to be part of this. Hope all of you will find this useful or found this useful. And thank you for the opportunity. Thank you all.
Thank you so much, ma'am. I request everyone to please mark your attendance if you haven't marked it yet, and to please leave the meeting. Thank you.
Thank you so much, ma'am.